Welcome to this session of fluid machines. In today's tutorial class, we are going to solve few representative problems related to principle of similarity and dimensional analysis in rotodynamic machines. So, before solving problems, I will quickly go through the important dimensionless parameters that may arrive in rotodynamic machines. So, the topic is principle of similarity and dimensional analysis. In rotodynamic machines. So, the physical parameters of rotodynamic machines which are very much relevant in this problems are the diameter of the rotor, the speed of the rotor, the flow rate Q through the rotor, Gh, where G is the acceleration due to gravity and H is the head across the rotor, rho the density of the fluid, mu the viscosity of the fluid, E the coefficient of elasticity of the fluid, and power transfer. So, using Buckingham's Pi-Theorem, one can obtain 5 dimensionless parameters which are very much relevant in this course. So, using Buckingham's Pi-Theorem, we obtained the first term being the pi 1 is q divided by n d cube, which is known as discharge or flow coefficient. The second pi term, which is pi 2, is Gh by n square d square. This is known as head coefficient. Third pi term is pi 3, rho n d square by mu or n d square by nu, where nu is the kinematic viscosity. This is Reynolds number. The fourth pi term is power transfer P divided by rho n cube d to the power 5, which is known as power coefficient. And the last pi term is E by rho divided by n square d square. So, these 5 pi terms govern the different characteristics of rotodynamic machines. Now, I am going to solve 2 problems related to this principle of similarity, and the first problem is related to one centrifugal pump. So, let me just read the first problem. So, a centrifugal pump handles liquid whose kinematic viscosity is 3 times that of water. The dimensionless specific speed of the pump is 0.183 and it has to discharge at a rate 2 meter cube per second of liquid against a total head of 15 meter. Determine the speed, test head and flow rate for a 1/4 scale model investigation of the full size pump if the model uses water. So, let me just list the important given parameters associated with this problem. So, the prototype centrifugal pump, for prototype pump it is given that the specific speed, the dimensionless specific speed is 0.183. So KSP is 0.183. The flow rate through the prototype pump is 2 meter cube per second. So QP is 2 meter cube per second, and total head across the pump is 15 meter. So HP is 15 meter. So important thing to note that here we are using subscript P to denote the parameters or variables associated with prototype. Similarly, the given parameters for model pump. So the kinematic viscosity for the model is 1/3 to that of prototype. Here it is specified that the centrifugal pump handles liquid whose kinematic viscosity is 3 times to that of water. Now the model is using water and the prototype pump uses some other fluid having kinematic viscosity 3 times. So model kinematic viscosity will be 1/3 to that of kinematic viscosity of prototype. Another important thing to note here is that we are using a 1/4 scale model. So rotor diameter of the model will be 1/4 of the diameter of the prototype. So these are given quantities. Now we have to determine the speed, test head and flow rate for a 1/4 scale model. So speed of the model, test head of the model and flow rate. These 3 quantities are of interest. Now let us first start with determination of speed of the prototype pump. Now we know that the specific speed of pump is given by the speed of the pump times the flow rate to the power half divided by GHP to the power 3/4. So using this relation we can obtain the speed of the prototype pump as specific speed times GHP to the power 3/4 divided by QP to the power half. Now we substitute the given quantities. So 0.183 is the specific dimensionless specific speed, G is 9.81, HP is given as 15 whole to the power 3/4 divided by QP is 15 to the power half. So we can obtain the numerical value of specific speed as, so QSP is 0.183 times 9.81 into 15 to the power 3/4 divided by 15 to the power half. This will be, or rather this is NP. So specific speed is 0.183. Now we are going to determine the speed of the prototype rotor. So NP will be 5.47 revolution per second. So one desired quantity is now has been obtained as 5.47 revolutions per second. Now we will determine the second quantity of interest, which is the speed of the model pump. Now to determine this we will use the principle of similarity by equating the Reynolds number. Reynolds number. Reynolds number is nothing but the pi3 term that we have previously obtained in here. So, this pi3 term is the Reynolds number. So, this is n d square by nu, n d square by nu. So, pi3 of model will be pi3 of prototype according to the principle of similarity. Now, we substitute the expression for pi3. So, nm dm square by nu m will be equal to np dp square by nu p. So, using this we can obtain the speed of model as np times nu m by nu p dp by dm square. Now, we substitute respective numerical values given to obtain nm. So, nm will be np we have obtained as 5.47, nu m by nu p. So, previously you have noted that nu m is nothing but nu p by 3. So, kinematic viscosity of model is 1/3 of the kinematic viscosity of prototype. Now, we will substitute nu m by nu p is equals to 1 by 3 here. So, here nu m by nu p will be 1/3 and dp by dm. So, as per the prescription of the problem, dm is 1/4 of the dp. So, diameter of the model pump is 1/4 of the diameter of the prototype pump. So, dm by dp. So, from here we obtain dm by dp is equals to 1/4. So, here we will substitute dp by dm to be 4. So, this gives the nm as 29.15 revolutions per second. So, speed of the model centrifugal pump will be 29.15 revolution per second. Now, we will determine the head or the test head across the test head for the model pump which is HM. To determine this, we make use of the head coefficient or equality of head coefficient. Equality of head coefficient gives. So, head coefficient previously we have defined as pi2, which is gh by n square d square. So, we will make use of this relation. So, pi2 is gh by n square d square. So, pi2 of model will be pi2 of prototype. This is according to principle of similarity. Now, I will substitute the expression for pi2. So, ghm by nm square dm square equals to ghp by np square dp square. This will give hm equals HP times Nm by Np square and dm by dp square. So HP is previously specified in the problem as 15 meter. So I am going to replace this. So 15 meter. Nm we have obtained as 29.15 revolution per second. So 29.15. Np is also obtained previously as 5.47 revolution per second. So Np is 5.47 whole square, and dm by dp is equals to 1 by 4. So 1 by 4 square. This will give Hm as 26.64 meter. So the head for the model pump is 26.64 meter. Now another important quantity of interest is the flow through the model pump. Now to obtain this flow, I am going to use the flow coefficient. So flow coefficient was previously obtained as this pi1 term. So q by n d cube. So this flow coefficient is pi1 equals to q by n d cube. Now equality of flow coefficient gives pi1 m equals to pi1 p, or qm by nm dm cube equals qp by np dp cube, or qm equals qp times nm by np into dm by dp cube. Now qp, the flow through the prototype pump is given as 2 meter cube per second. So 2 nm, so nm we have obtained previously. So nm is 29.15. So nm is 29.15. np is 5.47. np is 5.47 and dm by dp is 1 by 4 cube. So flow through the model pump can be obtained here as 1.166 meter cube per second. So qm is 0.166 meter cube per second. So we have determined all the three important quantities that we were intending to obtain, that was Nm, Hm and Qm. Now I am going to solve another problem related to turbine. So this is the second problem, problem 2. So I will just read the problem first. Say a quarter scale turbine model is tested under a head of 10.8 meter. The full scale turbine is required to work under a head of 30 meter and to run at 7.14 revolution per second. At what speed must the model be run? If it develops 100 kilowatt and uses 1.085 meter cube of water per second at this speed, what power will be obtained from the full scale turbine? The efficiency of the full scale turbine being 3% greater than that of the model. Now what is the dimensionless specific speed of the full scale turbine? So let us first list the important given quantities. So for model, the model is tested under a head of 10.8 meter. So head is 10.8 meter and power produced by the model is 100 kilowatt, where the flow rate through the model is 1.085 meter cube per second. And it has been mentioned that the quarter scale turbine model, that means diameter of the model will be 1/4 of the diameter of the prototype. Now for prototype turbine, the head is specified as 30 meter and the speed of the prototype turbine is given as 7.14 revolution per second. Important quantities of interest are power of the turbine, prototype turbine, and the specific speed, dimensionless specific speed. Now as the head for the model and prototype are given and speed of the prototype are given, we can easily obtain the speed of the model by using the equality of head coefficient. So equality of head coefficient, this is, so head coefficient is the pi 2 term, which is gh by n square d square. So pi 2 of model will be pi 2 of pump or prototype. Now substituting the expressions, we can obtain the gh of model hm nm square dm square will be ghp by np square dp square. So np, hp and hm are known, so only unknown is nm. So nm will be np times dp by dm root over of hm by hp. Now I will substitute the value of np as 7.14. So np is 7.14, dm by dp is 1/4. So dp by dm is 4, hm is given as 10.8 and hp is given as 30. So this will give nm 17.14 revolution per second. So nm, the speed of the model turbine, is 17.14 revolution per second. Now before obtaining the power, which is our main interest, the power output from the prototype turbine, I am going to calculate the flow through the prototype turbine by using the equality of flow coefficient. Equality of flow coefficient. Flow coefficient was previously obtained as pi 1 equals to q by n d cube. So equality will give pi 1 m is equals to pi 1 p. So qm by nm dm cube is equals to qp by np dp cube. So from here we can obtain qp as qm times np by nm dp by dm cube. Now substituting different quantities, we can obtain qp as qm is given as 1.085 meter cube per second, np is given as 7.14, nm is obtained as 17.14 and dp by dm is 4. So this cube, this will be 28.93 meter cube per second. Now to obtain power of the prototype turbine, one very important thing to note here is that the efficiency of the full scale turbine is 3% greater than the model. So to obtain the power, let us first obtain the efficiency of the prototype turbine. So efficiency of the prototype turbine np will be nm, which is the efficiency of the model turbine, plus 0.3 times nm. Now nm is power output by the model pm, so pm divided by rho q gh, so rho m qm hm. Power output from the model turbine is 100 kilowatt. Density is for water 1000. qm is 1.085 meter cube per second. G is 9.81. hm is 10.8. So this gives efficiency of the model as 8.76. So efficiency of the prototype will be 0.87, sorry, this is 0.87 plus 3 times 0.87, which is 0.9. So this is the efficiency of the prototype turbine. Therefore power output from the prototype turbine will be efficiency of the prototype turbine times the rho qpg hp. Now substituting different quantities, power from the prototype turbine can be obtained as efficiency is 0.9, rho is 10 cube, qp we have obtained, so 28.93, g is 9.81 and h is given as 30 meter. So this will give 7.66 megawatt. The last quantity of interest is the specific dimensionless specific speed. Or NST, which is NP PP to the power half by rho to the power half GHP to the power of 5 by 4. This is the expression for specific speed, dimensionless specific speed of the prototype machine. Now substituting different quantities, we can obtain the NP is 7.14, power is 7.66 times 10 to the power 6 whole to the power 1 by 2, rho is 10 cube to the power half, G is 9.81, HP is 30 over 5 by 4. This will be obtained as 0.513. So the sign for this will be more appropriate, will be KST, So, dimensionless specific speed of the turbine will be 0.513. Now, important fact to note here is that here to determine the power of the prototype turbine, we are not using the equality of the power coefficient. This is because here it has been mentioned that the efficiency of the prototype turbine is not same as the model turbine. So, we know that the hydraulic efficiency is nothing but, so eta hydraulic efficiency we can write in terms of pi terms. So, this is pi 4 by pi 1 pi 2. So, hydraulic efficiency, equality of hydraulic efficiency means all the terms will be same for model and prototype, but in this case efficiency of model and prototype are not equal, and we have previously used equality of pi 1 and pi 2 in terms of equality of discharge coefficient and head coefficient. So, pi 4, which is the coefficient power coefficient, will not be same for the model and prototype. That is why we have used the efficiency of model turbine and then obtained the power in this way. So, with this I am ending today's lecture. Thank you.